Hello and welcome to our soil results presentation. Please ensure that the report is read in full before implementing any of the recommendations we suggest. The first section of our reports consists of 4 separate tests that were run to help identify the soil on site, as well as its relationship with water. The first 2 tests, cone fall and thread rolling, were performed on the material that had passed through a 425 micron sieve. The effect of this will be explained later. A cone fall test was performed to determine the liquid limit of the soil. This is the first step in finding the plasticity index, a value that is essential to understanding how the soil can be compacted. After running a series of 4 trials, the liquid limit at a 20 mm penetration depth was found to be 35.42%. The thread rolling test was also performed 4 times to determine the plastic limit of the soil, which is the boundary between the plastic and semi-solid states of consistency. Our average plastic limit was found to be 22.6% water content. With these values, we were able to determine the plasticity index at 8.82% water content. This is a good indicator of the soil's compressibility. The PI reflects how much the soil will swell and shrink over time. The higher the plasticity index, the higher the possibility of swelling and shrinkage. This means overall that there is a low chance our soil will sink or displace when being built on. This test was carried out on a 1 kilogram sample of soil taken from site. It was found that 9% of the soil was smaller than 0.425 microns, meaning that the 2 previous tests run on the soil for Atterberg's limits were carried out on only a small percentage of the soil. This should be kept in mind considering it does not account for the behavior of the other 91% of soil. The grain size distribution chart was used to determine the USCS classification for our soil. We determined it to be well-graded gravel with a coefficient of uniformity at 9.069 and a coefficient of curvature at 1.526. Research shows that well-graded gravel was a good soil to build on as it's a large bearing capacity, a small settlement, and is easy to compact. The standard Proctor compaction test is used to find the moisture density relationship. This is done by compressing a soil sample at different water contents and finding the dry soil density. This allows you to easily see how the stability of a soil sample changes over a varying water content. These graphs are the saturated soil density and the dry soil density plotted against the water content as a percentage. You'll notice there are 2 lines on each graph, one indicating the theoretical water content and one indicating the measured water content. The results show a maximum dry density of the soil is 1,975 kilograms per meter cubed at a water content of around 12%. Meaning that the structure of the soil will start to deteriorate above 12% water. However, our results show that the soil can keep its structural integrity in the water content up to 15%. This is more than enough to support the building loads, as it is highly unlikely we will reach such a high content. We created a Geo5 model to represent the layer of varied materials found from the boreholes. It shows gravelly sand, which is made from ground, mudstone in the Crackington Foundation, and a lens of silty clay, also in the Crackington Foundation. A Belgian cement factory requires the clay on a new site to be removed in order to get to the limestone deposit below. Our main aims are to find the shear strength of the clay using different normal stresses to plan the proper disposal method for the overburden so we can reach the limestone. As expected, the results show that with an increasing normal stress, a higher peak shear stress and critical stresses are measured respectively. As previously mentioned, the higher normal stresses yield higher peak and critical shear stress. The graph shows these results and demonstrates how the soil follows the general expected shape. Using the results from the 4 different tests, the data was then extrapolated and linearized where needed. The equation of the lines were obtained through Excel, which yield the parameters of the soil. we found the peak stress cohesion coefficient to be 72.88 kilopascals, while the cohesion angle phi to be 21.78 degrees. For critical shear stress, it was found that the cohesion coefficient is 53.86 kPa, while the cohesion angle being 17.78 degrees. These parameters indicate that the soil is classified as a soft clay, meaning disposal can be done with a scraper or digger, with the material being able to be reused either on site or taken to a proper disposal centre. Triaxial testing is used in order to model the long-term behaviour of soil, in particular of soil in a slope. For this test, we were testing it in CU conditions. We were able to use the data provided to manipulate the figures in Excel into plotting our Mohr circles and finding the angles at the tangent. From the Mohr circle of total stress, we were able to observe a cohesion of 0, which has been calculated along the tangent using a gradient of 5.7, giving us an epsilon value of 9.9 degrees. We then observe an effective stress cohesion value of 21 kilopascals, which has been calculated using a gradient of 2.62, resulting in a critical angle of 20.9 degrees, a value we would expect in saturated clay. This cohesion value is high enough that we would expect to have a sticky clay, therefore on the slope we could withstand a high loading value. On the left, we observe the uncut graph for deviated stress and axial strain. The loading behaviors are as expected until failure. We found failure at the deviated stress value 183 kPa, 265 kPa, and 277 kPa respectively. This makes sense as the samples under higher pressure failed sooner. Because they are restrained samples, they will not fail completely, leading to the long tails observed. For pore pressure versus axial strain, we are looking to find the point where the line's gradient tends towards 0, hence reaching the critical state. We can observe this between 0.08 and 0.11 for the 600 and 400K samples. However, we will notice that they do leave this region after a certain point, meaning that we cannot be entirely clear where any of our samples enter critical state. We observe that the PQ graph and the P-Q graphs failing along the same gradient, which is our critical state line. We have calculated the critical state angle to be 20.8 degrees, almost the same as the value calculated using Mohr's circle. We have had to cut the 600K line for P-, where the Q value was 374 kPa. This is because the line was tending back towards the x-axis, another example of the sample not failing correctly. In order to linearize our P- values, we decided to log them. We then plotted that against the specific volume, which was calculated using the final water content given. This resulted in our lines of P being plotted against a constant linear value. Note that the 400K line does not line up with 200 and 600. However, the ends of both of those line up. This could perhaps again be due to the sample not being able to fail completely due to the restraints.